There's another use for chemical equations, and this is reaction stoichiometry. Now, to do reaction stoichiometry, you need a modified form of chemical equation, a balanced chemical equation. Now, not all chemical equations need to be balanced. All the stuff we just did, I didn't bother to balance any of those equations, and it was quite useful to predict products or to capture what I'm seeing. But in addition to a chemical equation, we can take it to the next level and form a balanced chemical equation. What's different between a chemical equation and a balanced chemical equation are those numbers in red in front of the substances. These are coefficients. Coefficients are added to an equation to balance the chemical equation. Now, what do the coefficients mean? Well, when we read an equation, again, the first purpose of those formulas is stand-ins for the names of the substances. That first compound is known as propane. The next one is oxygen. The next one is CO2, and water is the last one. The formulas just take the place of those. But if we add coefficients, we're saying so much more than just what substances went into the pot and what came out of the pot. If I add coefficients to it, there's a lot more information that becomes available. The first information is that I am now telling you the ratio of the particles as they react. If I take a look at the particles involved in this, propane has got 3 carbons and it's got 8 hydrogens attached to it. It's a complex molecule. Oxygen, you know, is just 2 oxygen atoms fused to each other. What these coefficients are telling me is for every 1 propane, I need 5 oxygens to do this reaction. And what I get out on the other side is going to be 3 CO2s and 4 water molecules. When I add those coefficients, I'm now exploring on the design level, on the atomic and molecular level, what's actually happening. And I'm taking stock of the atoms that are being traded as we go along. In other words, I'm counting for the fact that this 1 molecule requires 5 molecules of oxygen in order to react. And its components, that with each tick of the clock on this reaction, I'm consuming propane, which brings to the party 3 carbons and 8 oxygens, and I am consuming 5 oxygen molecules, which means I'm contributing 10 oxygen atoms. And the term balanced is because if you look at the other side, there's still 10 oxygen atoms. 6 of them are in those 3 CO2s, and 4 of them are in the waters. And then if you look at the hydrogen and the carbon, you'll see that the same number of atoms are on both sides of that arrow. Now, if this ratio of atoms is true, when I look at the numbers in that balanced chemical equation, which represent the number of molecules, well, if it's true for 1 molecule and 5, it's going to be true for 2 and 10, or it's going to be true for 4 and 20. It's going to scale up. And as you've already discovered, when chemists want to scale up from the molecular level to the laboratory level, they scale up in a count of atoms that is equal to Avogadro's number, moles. We do that because of the simplicity of the mass relationships between the AMU and the gram. So if 1 molecule of propane needs 5 molecules of water, then it's going to necessarily be true that 1 mole of propane is going to need 5 moles of water. And if we know that, then we can convert it into quantities that we can look in at the laboratory. We can calculate the molar mass of each of these, and from that, know the mass that we are working with in the laboratory. How much propane do I have to measure out, and how much water do I have to measure out to make this work? Now, one huge distinction is those numbers in red. Those numbers in red, those coefficients, are just ratios of substances. Don't confuse them with subscripts. As we go through and balance these equations, we will be adjusting those coefficients to find a balance. And you're going to be tempted to change a subscript at some point. Never change the subscript. The subscript is part of the personality. Oxygen comes in a 2-pack. This reaction is using molecular oxygen. If I change that to O3, it would be a different substance, ozone, and the chemical reactivity would not apply. So as we balance these equations, you will be adjusting the coefficients to find the balanced chemical equation. But never touch the subscripts. Those are locked in as soon as you recognized you were working with molecular oxygen or propane or CO2 or water. All right, so how do you find that balanced chemical equation? There's a couple different approaches to this. My suggestion when you're finding a balanced chemical equation is to be methodical about it and to record each step as you go through. And this way, if you make a mistake, you can always unwind it, go back one step. And I'll tell you right now, the number of steps that it'll take to balance equation, well, it shouldn't be more than the number of components in the reaction. If you have 2 reactants and 2 products, you should be able to do this in 4 steps. If you find yourself on step 8 or step 9, you're kind of spiraling. And you may be at a point where if you keep working with that equation, there may be an error in it at this point. You may never be able to get to a balanced chemical equation. So if you've got 5 components in your reaction, make sure that you are, if you go past 5 steps, question where you're at. You may want to take 2 steps back to and start from that place. Because you may be in a place that you're not going to be able to get back from. All right. And some tips to win here. In general, what I do is I'd start by putting an arrow on the paper and putting the reactants and products. Then I'd convert those into the chemical formulas that I'm going to use. Then I would take stock, take a look at how many atoms I have on the reactant side and the product side of each material, and then begin iterating. What I would do is I would rewrite the equation below it. You can just rewrite the coefficients. You don't have to write the formulas each time. In the examples I'm going to show you, I write the formulas, but you can just write the coefficients in the next line. But do that and change 1 coefficient. And I strongly encourage you to only change 1 coefficient at a time. If you start juggling 2 or 3 coefficients, you're not doing the work on the paper. You're doing it in your head. Maybe you can juggle these things in your head for the simpler ones. It happens. It's totally possible. But if you do it on the paper, if you make a mistake, 2 things happen. 1 is you're more likely to catch your own mistake and fix it. And 2 is if you turn it in, whoever's reading that can see where you made a mistake. They can give you partial credit for the rest of it. But change 1 coefficient at a time until you get to a point where you have the same atoms on the left, the same atoms on the right. The coefficients you discover in that way will reveal the balanced chemical equation. Some tricks to work with. 1 is always start with the most complicated molecule. Now, I don't mean balance its coefficient. I mean look at that most balanced, most complicated molecule and use it as a shopping list of the elements and the atoms that you want to balance. Another is always save the simplest molecules for last. That's usually oxygen or hydrogen. And even if it's not oxygen or hydrogen, if all of the molecules have oxygen or hydrogen in them, still save that element for last. You may not even have to balance it. If all of the molecules have hydrogen in it and you save hydrogen for last, when you balance all the other atoms, you'll probably balance the hydrogen. Another thing is you will have to iterate. There will be times when you will get down to step 3 and you say, that was the wrong choice. I got to step back 1. That's okay. That's why you do it in steps, so you can rewind more easily if you need to. Another thing is when you're working with polyatomic ions like sulfate or phosphate, instead of balancing the atoms, phosphorus and oxygen, you can just balance those as a cluster because they will because they're not going to break down in that system. You can treat them like another kind of atom. Another thing is don't be afraid to use fractions. If you get to a situation where you need 3 oxygens and you're looking at O2, well, just say 3 out of 2, 3 out of a 2-pack, use 3 halves there. In this way, you're not juggling a lot of calculations. You have to balance multiple substituents at the same time. And if you do use fractions, for now, when you get to the last line, look at the denominators in any fractions you introduce, multiply everything by that denominator. So you end up with the smallest whole number multiples as coefficients. So it's okay to use fractions. Just don't leave it in fractions for now. There will be some situations, mostly next semester, maybe a few this semester, where you will have to leave it in fractions. We'll talk about those situations when we get to it. But in general, it'll make your life easier if the coefficients are smaller whole number multiples. You want to try a couple? Here, I got one for you. Here's a simple one. Diphosphorus trioxide is formed by direct combination of its elements. Balance the chemical equation. Okay, so diphosphorus trioxide, is that a reactant or a product? It's the first thing in the sentence, but is it a reactant or a product? I'm forming it, right? So that means it's a product. And the elements that I'm forming it from, well, this one's pretty straightforward. I'm forming it from oxygen and phosphorus. So I can go through and capture these pieces just by writing the words on the paper. So now I've got a skeleton to show me what's happening here. Oxygen and phosphorus come together to form diphosphorus trioxide. Now, before you can work with this, you need to get into the formulas. Formula for oxygen is O2. What's the formula for phosphorus? There are different kinds of phosphorus, but if anyone ever asks you what the formula is, phosphorus and sulfur, the two polyatomic elements that you know the formula for, sulfur is S8, phosphorus is P4. Now, diphosphorus trioxide, that's a binary compound. Be careful, that's a binary compound of two nonmetals. What's the formula for diphosphorus trioxide? Diphosphorus, two phosphoruses. Trioxide, three oxygens. So P2O3. Okay, now I have my formula as, now I have my equation using chemical formulas. Next step up is to kind of take stock, see where I'm at. If I take stock on this, you'll see that, and the way I like to do this is just draw a line with an R above it and a P below it, reactants and products, and then just kind of make columns for the things I'm balancing. In this case, oxygen and phosphorus. Those are the only elements in play right now. If you take a look, P4, one P4 means there are 4 oxygen atoms on the left-hand side, the reactant side. And on the product side, I got P2O3, there are 2 phosphorus atoms. So that's not balanced. And for the oxygen, I got 2 and 3. That's not balanced either. All right. If you want to balance the system, take a look at the most complicated molecule, P2O3, use it as a shopping list, balance its elements one at a time. The first thing I'm going to do, well, I could balance the phosphorus and the oxygen, but I'm going to save oxygen for last. Usually, if you save oxygen for last, you will have less headaches. So to balance these, I need to change the coefficient. If I look at each of those elements as, the first one, oxygen, the second one, phosphorus, the third one, P2O3, which coefficient do you want to change to balance the phosphorus? If I look at that first column as A, next is B, next is C, I'm going to balance C because I can change the coefficient in front of P2O3 to a 2. And now I got 4 phosphoruses on both sides. All right. If I take stock, my phosphoruses are now balanced. The oxygens are not balanced. So now I'm good. And by the way, you don't have to write the formulas each time. You can just write 1, 1, 2 underneath that to keep track. All right, for the next line, what element do you want to balance next? Oxygen, well, phosphorus is done, so oxygen is all that's left. How can I balance the oxygen in this? Which coefficient do I change? The first one, the second one, or the third one? Well, I got 6 oxygens on the right side now because it's P2O3, but I got 2 of them, so 6 oxygen atoms. On the left side, I have oxygen molecules that come in a 2-pack. So to get 6 on my reactant side, I'm going to put a 3 in front of the oxygen. And if I take stock, now everything's balanced. Okay, balancing chemical equations is going to be an important trick. You're going to be doing this. If you get a job doing chemistry, you're going to be doing this literally every day. But finding those balanced chemical equations opens up a lot of opportunities for us. Anyway, that's an easy one. You want to try a harder one? Let me give you a harder one. So here I've got phosphoric acid and calcium hydroxide. They're reacting to form water and calcium phosphate. That's a ton of stuff there. And you've got to be careful when you read this. It's not always the case that the first thing you encounter in the sentence is a reactant, the last thing is a product. They can get mixed up. You have to read it carefully. So what I like to do is I like to put an arrow in the middle and then just go through, and as I encounter each one of those substances, either put it on the left or the right, depending on its case. Phosphoric acid and calcium hydroxide are my reactants here, and water and calcium phosphate are the products. If I go through and use the tricks that we had in the last chapter to find the name of the formula of each of those, I get these formulas. Now, you might look at that one and say, that's a lot more complicated than P2O3. But it's actually not that much more complicated. Part of the trick here to make this simpler is to treat those phosphates as a single unit. In other words, I'm not going to balance phosphorus and oxygen separately. I'm going to balance, for example, the phosphate ion. And then I will balance the other oxygens in the molecule, hydrogen and calcium. Go through and take stock, find out, how many phosphates I have, how many calciums I have on the reactant side and the product side. And then I'll go through and try to do my first line. Now, looking at that equation, what looks to be the most complicated molecule or substance in that system? What do you think? Well, it's not water. Water's just 2 elements. That's going to be an easy one to balance. The phosphoric acid is really just 2 elements again, because I'm using the phosphate as a single thing. It's just hydrogen and phosphate. So I'm going to save that one too. Calcium hydroxide, you can argue that's getting more complicated. That calcium phosphate's the one I would probably pick. So I'm going to zoom in on that calcium phosphate. I'm going to look at what it's made of. Calcium and the phosphate ions. I'm going to treat the phosphate not as phosphorus and oxygen, but each phosphate as a package of its own. I'm going to try and balance the phosphate first. Now, the phosphate, right now, I have 1 phosphate on my reactant side and 2 on my product side. Considering each one of those reagents as A, B, C, and D, which coefficient do you want to change first? The coefficient at A, at B, at C, or D? Which one will let you balance the phosphates? Well, there's 2 legit answers there, but I suggest you don't use a half in front of the second one. I suggest you use whole number multiples where you can. And if I put a 2 in front of the phosphoric acid, now my phosphates are balanced. And like I said, you can just rewrite this line as 2, 1, 1, 1 to save a little bit of space and a little bit of pencil lead. I tend to write out the whole thing, but that also kind of helps me look at some other things as I'm going along. If I go through and balance this, take stock, I now see that the phosphates are balanced on both sides. It also changed the hydrogens. See how the hydrogen number is different now too? This is one of the reasons why you save hydrogen and oxygen for last. They get touched a lot. They get mixed up a lot as you balance other elements. So by saving them for last, you're less likely to mess up all those other elements. Okay, so I balanced the hydrogen and I balanced the phosphate in the calcium phosphate, but I'm not done with it. That's my shopping list. I balanced the phosphate. In order to get that complicated molecule off the table, I need to balance the other half, in this case, the calcium. I take a look at the calcium, and the calcium's got 1 on the reactant side and 3 on the product side. So to balance this again, I'm going to bring down those same coefficients, 2, 1, 1, 1, but I'm going to change one of them. I'm going to change the second coefficient to a 3. And when I do that, now the calciums are balanced. And again, I encourage you to don't try and do this all in your head. Don't do it in one step. Show the work, write it out each time. If you take stock here, you'll now see that the calcium and the phosphates are balanced. Let's see, but my hydrogen and my oxygen are not balanced. Okay, my hydrogen and oxygen are not balanced. It looks like I've got 12 hydrogens on the reactant side and 2 on the product side, 6 oxygens on the reactant side and 1 on the product side. At this point, there's one molecule that has hydrogen and oxygen in it. And if I take a look at that water, if I put a coefficient of 6 in front of it, now all my elements are balanced. So able to do that one in 3 steps. Sometimes it'll take 4. Shouldn't take 5, but if it takes 5, not a big deal. If you take 6 or 7 or 8, you're spiraling. Go back. Don't keep marching forward. I've seen students literally chew up a half an hour on one thing, just continuing to spiral. That's because they made a mistake in the first line. So if you made a mistake, or if you get to lines like 6 or 7, go back and look for that mistake, and then erase the stuff out of the mistake and take off from there, and you will be in a much better place. All right, this is balance. This is one way to balance the chemical equations. There's another trick. You want to see another one? One that might be a little more challenging? Let me give you one more to play with here. This is a combustion reaction. When you see combustion reactions, again, a combustion reaction is when you take some substance, react it with oxygen, get out the fully oxygenated forms. So, for example, ethane. The formula for ethane, you're not responsible for ethane, but I would put down ethane, I would put down oxygen, and then the fully oxygenated forms. And you are responsible for knowing combustion reactions produce CO2, H2O, NO2, P2O5, the fully oxygenated form of the elements in that original substance. In the case of ethane, we're looking at C2H6. And again, you're not responsible for that formula. It'll be given on a test. Oxygen is O2, carbon dioxide is CO2, and water is H2O. Now, if I go through and I look at the stock on this, you'll see that, well, it's just carbon, hydrogen, oxygen. Seems pretty straightforward. My suggestion is look for the most complicated molecule. Which one of these do you think is the most complicated molecule? The one I should use as my shopping list, my hit list for elements to balance. Yeah, I agree. That ethane, I mean, the others, H2O, CO2, first of all, they all have oxygen in it, so I'm likely going to save that for last. But that C2H6 looks like the more complicated one. And within it, I'm going to choose to balance carbon first. So I've got 2 carbons on the right side and 1 carbon on the product side. Now I could balance it by putting a 1/2 in front of the ethane, but again, don't use fractions unless you have to. And so I'm going to put a 2 in front of the CO2. If I take stock, now my carbons are balanced. The hydrogens, well, I have 6 on the reactant side, 2 on the product side, and the oxygens, 2 and 5. save oxygen for last. If for no other reason, then you see that the substance in the second column is pure oxygen. That means I can adjust the amount of oxygen without disturbing any of the other elements. So always save oxygen and hydrogen for last. And if you got to do both of them, well, look to see if you're working with H2 or O2. Save the pure element for last. Now I can balance the hydrogens because on one side I've got C2H6 and on the other side I got H2O. Which coefficient do you think I want to change to balance the hydrogens? Do you see if I just put a 3 in front of that H2O, now I have 6 hydrogens on both sides? And if I take stock here, my carbon and my hydrogen is balanced. Now my oxygen is still unbalanced. On the left side, I've got 2 oxygens, O2. And on the right side, I've got 3 waters, that's 3 oxygens, and 2 CO2s, that's 4 oxygens. So 7 on the right side. So I want to balance one of the coefficients in order to get the same number on both sides. Well, if I change the coefficient on the water or the CO2, I'm going to mess up another element. But if I change it on the oxygen, well, then I'm done. I've balanced my chemical equation. But how do I get 7 oxygens out of O2? Do you guys see the trick? So like I said, don't use fractions unless you need to. But when you need to, use fractions. So I take a look at that oxygen and I say, well, I need 7 out of a 2-pack. I'm just going to write 7 halves, 7 over 2, 7 oxygen atoms out of a 2-pack. And now my system is balanced. And if you look at the numbers, they're balanced across. And that is a balanced chemical equation. Now, my suggestion to you is don't leave fractions in the final equation if you don't have to. It'll make the next step with what we do with these equations harder. Technically, it's balanced, and there will be some cases where you won't have a choice. You will have to leave it in fractions. But for now, you're not going to have to. Just take a look. If it's 7 halves, then just multiply that by 2. And at the same time, multiply everything else by 2. So take one extra step to multiply everything by 2, and you end up with 2, 7, 4, and 6. And that's your balanced chemical equation. You can check the numbers, put a box around it, you're good to go. All right, so balancing chemical equations it's going to take some getting used to. But if you use these tricks and use these steps, you will be able to balance most of the chemical equations in this class in a limited number of steps. If you find yourself on step 9 or step 10, you made a mistake. Go back and find the mistake and start from that point. You will get to the answer quicker than if you keep crunching when you're out in left field. Okay, so balanced chemical equations. Balanced chemical equations are our starting point. Balanced chemical equations are our starting point for doing reaction stoichiometry. Now, you've been doing stoichiometry up till now, but we've been doing stoichiometry. Let's be clear on this. What is stoichiometry? Stoichiometry comes from, I believe it's the Greek. Metry, meter is to count, and stoich is element. So this is about counting elements. And you've already been counting elements when we're talking about, for example, how many atoms are in a gram of copper, or how many hydrogen atoms are in a mole of water. That is stoichiometry. But we're going to do a better trick. We're going to do stoichiometry not about a sample, but about the whole reaction. And this is where we use the balanced chemical equation. Because that balanced chemical equation gives us a ratio of atoms and molecules to each other in the reaction. And it therefore gives us a reaction when we scale it up to whole moles of that system. You always have to use a counting system when you're doing reaction stoichiometry, but you can get into or out of that system by using into or out of that system by using grams to moles, moles to grams, or other conversion factors that are up and coming. Now, let me show you the trick to doing reaction stoichiometry. The trick is a factor called the mole ratio. Someone might ask you for this equation, if I burn 15 molecules of oxygen, well, how many molecules of water do I create? Now, that one's pretty simple. You can probably follow it in your head. You may even be able to do it without any math. But let's do it with math so that when it does get more complicated, we know the math to fall back to. So if I'm burning 5 oxygen molecules, and getting 4, then if I burn, well, 3 5s, I'm probably going to get 12 water molecules out the other side. In other words, if I start with 15, divide by 5 and multiply by 4, I'm going to get the number of water molecules. So that ratio in the center, that's just unity, because in this reaction, 4 waters equal 5 oxygens. So it's like saying 5 over 5. It's just unity. Therefore, 15 O2s equals 12 H2Os. I'm leveraging off of that unity as a conversion factor. And if I'm in a situation that I can't do in my head, like someone says 2.7 moles, that same trick works. I take 2.7 moles, I multiply it by 4 over 5, and I discover 2.2. I let the numbers talk to me. All right, that conversion factor in the center works. It also works if, for example, I want to find something else in the equation, maybe CO2. I just use a different conversion factor. 3 CO2s equal 5 oxygens. Or I could go to propane. The coefficient in front of propane isn't written there. If it's not written, assume 1. 1 propane equals 5 oxygens, a different conversion factor. All of these conversion factors, I think there's something like 4 factorial conversion factors in here. So maybe 12, maybe 24 different conversion factors. They're all contained in that balanced chemical equation. I can dance between any of those elements by using that balanced chemical equation. The conversion factor that takes us between these two is called the mole ratio. And the mole ratio is central to reaction stoichiometry. It's the key. It's how I go from a mole of any substance to a mole of another substance in that reaction. It doesn't mean going from reactants to products. I could go from one reactant to another reactant, or from one product to another product, or from a product to a reactant, or from a reactant to a product. And all of the conversion factors that are available to me, all the mole ratios I might use, I can read right off of that balanced chemical equation that we just worked on how to build. All right. Up till now, the type of stoichiometry we've been doing was within a particular substance. I told you I've got 2 grams of this. How many single molecules do I have? Used molar mass to go grams to moles and Avogadro's number to go moles to singles. Or maybe I gave you singles and said, well, how many grams? You just did the reverse conversion. You started with the given and used those conversion factors in a different order. But all of that stoichiometry, and then even expanding on that, when we went beyond copper, we did stoichiometry with water. And I didn't just ask you grams and moles and atoms, maybe our grams and moles and molecules. I may have asked you about the atoms within water. And you can use the chemical formula as another conversion factor. So you go from grams to moles with molar mass. You go from moles to molecules with Avogadro's number. And you can even use the chemical formula to go from molecules of water to atoms of hydrogen. And all of these conversions that we were working with last week, this is all stoichiometry. But here's where we get into reaction stoichiometry. Here's where the power really opens up. Now I'm not limited to just being within water. I can go from water to propane by using this new conversion factor. And with this new conversion factor, I can go from water to propane. And all the stuff I've been doing with water, I can do it with propane too. So there's a lot more power in stoichiometry when you take into consideration this mole ratio. When you go just from stoichiometry to reaction stoichiometry, there's a lot more questions you can answer. I can talk about burning grams of propane, and I can ask you how many atoms of hydrogen come out in the water that's being produced. I could go from single molecules of CO2 produced and find out how many grams of oxygen were consumed. I can dance all over this map. Now, we are going to spend most of our time above that dotted line. You go below the dotted line on the design scale, the scale of atoms and molecules, when you're figuring out a reaction or you're designing a reaction. When you're putting it to work, you spend most of your time above that line. So we're going to spend most of our time above that line, simplifying this map a little bit. And if we clean it up a little bit, it kind of looks like two arrows pointing at each other. Grams to moles to molecules, using molar mass and Avogadro's number, and the mole ratio to connect these two. This is the key to reaction stoichiometry. And if you read this on the internet or you read this in different books, you're going to see books that'll show you how to do a grams to moles calculation. Then they will show you how to do a grams to moles calculation. Then they'll show you how to do a grams to moles to molecules. They're going to show you like 16 different reactions, 16 different methods. But the reality is, you only need one. All you need to do is identify your starting point, figure out which square you're starting on, and then use the conversion factors, molar mass, mole ratio, or Avogadro's number, to move from one box to the next box, to the next box, to wherever you want to end up. And if you think of it like this, it's as simple, I mean, it looks as complicated as the New York subway or the Berlin subway, but it's actually as easy to get around as the New York subway. Just know what line to get on and what line to get off. What are the connections that you need to make? And there's really only three here: molar mass, mole ratio, and Avogadro's number. Would you like to try a couple? Okay, I got a couple ones here. Let's start with this one. Let's go back to our equation, burning propane. Somebody tells me, maybe I get this on the MCAT test, or maybe I get a job at the FBI, and they say, we need to give you a placement test before we know which group to put you in. Or maybe I want to take the GREs to get into grad school. There's going to be a question like this on any one of those tests. They say, how many moles of propane can you burn in 19.2 moles of oxygen? Do you see where we're going to start with this? I like to sketch that little two arrows facing each other, just a set of boxes on my piece of paper. And I circle where I'm going to start, and I put an X where I'm going to end. In this case, I'm just going from moles to moles. So it's going to be a short drive. But I'm going to start with moles of one substance, oxygen. I'm going to go to moles of another substance. Now, there's three conversion factors I might need: molar mass, mole ratio, or Avogadro's number. Which one do I need in this situation to go from moles of one substance to moles of another? Yep. Yeah, I'm going to use the mole ratio. You are correct. All right. So all I got to do is find the mole ratio for my particular situation. And I always like to write these as an equivalence so I don't bias myself. And if you write it as 1 over something else, you might stick it in the formula that way, even if it's not necessarily the way to stick it. So I always write it as an equivalence. 5 O2s equal 1 propane. Okay. Now comes the easy part. The hard part is, designing it, collecting your resources. It's like starting a business, coming up with your business design, collecting your investors. Actually crunching the business, that's the pleasure. Anyway, start with all scientific proofs. Start with something we all agree on. And we all agree we're starting with 19.2 moles. So I put that first. Then I put my mole ratio. In this case, I'm going to put the oxygen on the bottom and the propane on the top. So 1 propane on top, 5 on the bottom, crunch my numbers, watch my sig figs, make sure I put my units, check out it's reasonable, should be like 1/5 of that. So my calculator told me 3.84. Okay, I buy that. Put a box around it and I'm done. All right. Let's try move it up a notch. If in this problem, they're telling me I have 26.2 grams of carbon dioxide. So where am I going to start on my subway map here? I'm going to start in mass, right? So maybe I start in that top blue square. And what are they asking me? How many moles of propane am I going to need? So different substance. Go over to the purple side. And I'm going to be in moles. Do you see how this is just 2 steps? Grams to moles, moles to moles. Okay. So I like to sketch out a quick thing. Grams of carbon dioxide to moles of carbon dioxide to moles of propane. I like to sketch that out, just kind of like you might sketch out your subway trip ahead of time. Collect your terms. What's that first conversion factor? Going from grams to moles, moles to grams. What conversion factor am I going to need to go from grams to moles, moles to grams? That's molar mass, right? Now, can you find the molar mass of CO2 on a periodic table? You can't. But you can weigh a car on a bathroom scale. You just got to weigh it one piece at a time. It's the same thing with the molar mass of CO2. Look up the mass of carbon, which is on the periodic table. Oxygen, which is on the periodic table. 2 oxygen, each 16.00, that's 32.00. Add to it the weight of the carbon, 12.01. Now you got 44.01. Now you know the molar mass of carbon dioxide. 1 mole of carbon dioxide equals 44.01 grams. All right. Again, I like to write those as equivalences. That way, depending on which way I need to use it, I'm not biased. I can always, I have to think about what goes on the top, what goes on the bottom. I'm less likely to make a mistake by not thinking about it. And the other thing is I need a mole ratio. I need a mole ratio between CO2 and propane. Let's see. Propane's 1, CO2 looks like 3. So 1 propane equals 3 CO2s. Okay, now I got my tools. Now it's crunch time. I start with the extensive property. If I want to know an extensive property, my dimensional analysis has to start with an extensive property. 26.2 grams, multiply it by my first conversion factor. Grams go on the bottom because I started with grams, want to go to moles. Now I use the mole ratio. I'm consuming CO2, going to propane, put CO2 on the bottom. Actually, I'm producing CO2, but in my dimensional analysis, I'm getting rid of CO2, producing propane. Crunch my numbers, I get 0.198. Check your sig figs. That first measurement is 3 sig figs. The molar mass has 4, and that mole ratio, that's like how many corners there are in a square. You can see the corners on the square. You can see how many atoms are in your molecule, even if you're only working with a model of it. And if you can see the units, infinite significant figures. So the least of those is 3. Put a box around it. I'm good to go. All right. You want to try one more? I got one more. It's a little more complicated, then we can call it a day. All right. So here's one. Somebody tells me I got 24.2 grams of propane, and I want to know how many grams of water come out when I burn it. Okay, I can do that. Look at that map. Do you see how you're going from grams to grams? You're starting with the blue, the upper blue square, and you're going over to another substance, and you want it in grams, so you got to go to that upper purple square. That's 1, 2, 3 conversions. Grams to moles, moles to moles, moles to grams. And you don't have to learn a separate type of problem each time. You just need to find where you're starting, where you're ending, and connect the pieces like Legos. You do need a molar mass for propane. You can get that. We just did it in the last problem. You need a mole ratio. This is between propane and water now. So 1:4, 1 propane equals 4 waters. And then the last one, molar mass of water, 1802. 16 for the oxygen, 1.008 times 2 added together. That tells you 1801 for the, 1802 for the molar mass of water. That's the hard part. Collecting your resources, planning your trip. Now just enjoy your trip. Start with the extensive property and connect 1, 2, 3 conversion factors. Be careful. You wrote them as equivalences, so you got to decide what goes on the bottom. The first molar mass, the mass goes on the bottom, moles go on top. In the mole ratio, could go either way, but we're going from propane. So propane on the bottom, and then water on the top, and then get its coefficient, then use the coefficients from the balanced chemical equation. The last one, you're going back to mass. So this is a molar mass, but they're flipped. Now I'm going from moles to grams. So put 1 mole measures 1802 grams on the top. Crunch your numbers. That's what my calculator tells me, but my calculator doesn't know sig figs. I got to rein it in. There are 3 sig figs in what I started with, 4 in the measurement of 1 mole of propane, in the measurement of water at the end, also 4, and that mole ratio, infinite sig figs because it's a counting operation. So only 3 sig figs, slice it off after the 5, that gives me 39.6, put a box around it. Make sure you check your sig figs, check your units, and ask yourself if it's a reasonable number. All right. Okay, so this is reaction stoichiometry.